Okay, hello everyone. Let's continue the session. And the second talk of the second session of the afternoon will be from Louis Lemonnier, and he will talk about hypergraph simplification for linking the path sum approach to the ZH calculus. Louis, you have the floor.
Okay, thank you, Ross. So, as you said, we are going to talk about two powerful frameworks. So the path sum approach and the ZH calculus. At first, I'm going to introduce you to the path sum approach if you don't know it. It was well, I'm going to talk about path sum approach introduced by Matt 2 years ago in QPL 18. A path sum term is simply the well, a given scalar, a given phase polynomial, a given number of variables, and inputs and outputs. So this expression is very useful to express quantum circuits. It is also very easy to compose them to apply the tensor products. And also terms inside can algebraically simplify. So it is a very good framework for verification of quantum circuits. However, when you compute everything in a path sum and when all the terms simplify, it is nearly impossible to get a circuit back. For example, a z-gate is simply this expression with a phase of pi I x. If you compose two z-gates, you get a phase with a 2 pi. So this phase equal to 1, and it gives the identity. You would want to have the same with a Hadamard gate. So a Hadamard gate is the following, and to express it, you need to introduce another variable, which is y. So if you compose two Hadamard gates, you're going to introduce two different variables. So this does not simplify by itself. So Matt's idea was to create reduction rules to simplify these expressions. So what we're going to do is calculate the full path sum expressions of these two circuits, and simply tell that the expression of the first is going to reduce into the expression of the second, as follows. As you can see, we find these variables y0 and y1 introduced by these two h boxes, and the polynomial q must be Boolean, and it represents the output of the function f going into the first Hadamard gate. So those two those two Hadamard gates cancel, and this output of f replaces the output of the previous Hadamard gate, so it gives this expression. An example of use of this rule can be with this expression of a CNOT gate. If you compose two of them, you get this expression. Well, it's ugly, but don't worry. Here you can see that you can apply the HH rule on the two variables x2 and x3, and afterwards, every instances of x2 are going to be replaced with the variable x4, which gives this by reducing with the HH law. Those terms x0, x4 appear twice, so it simplifies by itself, so it's equal, and then you get the known expression for two following Hadamard gates, so it reduces to the identity. The Matt created two other rules, one inspired by this qubit equation. So if you concatenate 3 times sh, it is equal to the identity up to a scalar, and it gives this reduction rule, and also this qubit equation, which is kind of long and ugly, gives this path sum rule, which is also ugly. So I don't expect you to understand it. Now the aim of this talk is well, okay, sorry. The thing that you can realize is that the Maths software Feynman was able to reduce and to verify a lot of quantum circuits, and more that we could expect just looking at the inspiration of the circuits. So we could expect that the HH law and the other laws apply in a lot more cases than only what I have shown you. But the problem is, when you use those rules, and even if you are used to it, you don't really picture how they work. So that's why we are going to use the ZH calculus to picture how well the effects of those rules and how they actually apply. So ZH calculus was also introduced 2 years ago in QPL. So simply, it is the combination of two generators, the Z spider, also called white dots, and the H spider, also called H boxes. When you see an H box without a phase, it's actually an H box with a phase of -1, and a doubled H box is actually an exponential phase. The ZH calculus has its set of rules, proven complete also by Miriam and Alex 2 years ago. With the classical spider fusion, it has also a rule for fusion of H boxes, the classical cancellation of H boxes. You have here the cancellation. Sorry. Okay. The ZX by algebra and also a ZH by algebra, and some other rules that are not really important for my talk. And now what we're going to do is to translate path sum expressions into ZH diagrams, and also the other way around. The question you could ask right now is why was ZH calculus chosen? The reason for this is that the phase in the path sum term is actually this e to the 2 pi I phi, and phi is a polynomial, so it can be written as a sum of monomials, and a monomial is the product of a coefficient and variables. A sum inside an exponential is actually a product, and you can separate the constant terms with the variables. And if you remember the previous slides, you know that an H box is actually the same expression. So this complex number to the power of certain variables, and those variables are the inputs and the outputs of the H box. So it is precisely what we want to use to picture the phase of a path sum. Now I'm going to give you a concrete example of how you could translate a ZH diagram into a path sum term. Here, as you can see, you have a diagram with a negate dot. It's something that we like to use, but it's not really, well, it's difficult to translate it into path sum as itself. So we are going to use its definition. Then we are going to put white dots between every H boxes that have a wire between them. Okay. And we're also going to put white dots on every input and output wires. And then we have what we call a hypergraph-like diagram. So why hypergraph-like is if you consider white dots to be vertices and H boxes to be edges, you have a hypergraph, and you can only translate a ZH diagram into a path sum if it is hypergraph-like. So then, sorry. Okay. Then you can label the white dots with the variables. So this will be the variables of the path sum, and you get this expression. So if we consider x0 to be the output and x1 and x2 to be the inputs, you have five H boxes, so five monomials inside the face polynomial. The face polynomial with alpha is connected to those three variables, as we can see here, with beta connected to those three variables, and also the other. You can easily see that this algorithm can be done the other way around, because when you have this path sum expression, you can for each variable you can create white dots, and then put input or output wires if they are input or output, and you then link those white dots with H boxes, well, according to the phase polynomial. The main result of our paper is that one of the main results is that this translation is actually a bijection. So each hypergraph-like diagram has a corresponding path sum term, and it is also true the other way around. And something really important is that corresponding diagram and path sum represent the same matrix operator, so you don't actually change the operator doing this. Now that we're able to put ZH diagrams into path sum terms, we can try to understand the different applications of the HH rule. The first thing we want to try is to put two H boxes and put it into a path sum. Thankfully, it does what we want. Like this is the path sum of two Hadamard gates, so it simplifies to the identity. Now, if we consider this diagram, so it is the left-hand part, the left-hand side of the H-box fusion. If you put it in a hypergraph mode, you get this this path sum. On this path sum, you can apply the HH law on the variables x3 and x4, and doing this, so this instance of x3 is going to be replaced by x5 and x6, which gives this. So there is only one big monomial left, which gives this diagram, and this diagram is exactly what we wanted. So here we realize that the HH rule actually does the H-box fusion. Now, if we look at the ZX by algebra, we put so this side of the rule into a hypergraph-like mode, and we compute the path sum term, the corresponding path sum. We can apply the HH rule on x0 and x1, and here this instance of x1 is going to be replaced by the sum of x5 and x6, giving this, which gives this diagram. And this diagram is exactly what we would expect from the bialgebra. So we realize that the HH rule also does the ZX bialgebra. So, to summarize, the HH rule does the H-spider cancellation. It also does the H-spider fusion. It does the ZX bialgebra by pivoting, actually. So the HH actually applies a pivot on a graph. And so trust me, but it also does the ZX bialgebra. So we could think that it applies actually a hyperpivot on the hypergraph. Now that I'm sure, okay. Now that you've seen all this, I'm going to present you the more general results of the path sum rules into ZH. So for now, we've only seen examples, but we can actually picture the full rules into full equalities between diagrams into ZH calculus. First, I need to introduce you to bank boxes. So a bank box is this blue box around a part of the ZH diagram. And it means that what is inside this diagram is either not there, either once, either twice, etc. Bank boxes can be annotated and overlapped. So annotated, when you label this this bank box, it's oh okay, it actually shows it. Okay, it actually says that what is inside the bank box is every instance possible of the label, and when you overlap, well, okay. So this white dot is connected to something inside a 3 bank box, and also appears twice. So every white dot in the top is connected to three things, and the thing is copied twice. Well, I hope you are convinced that this is true. So in our way into picturing the HH rule, I'm going to show you a simpler example, which is when Q and R are Boolean polynomials. So they are XORs of monomials. And in this situation, so this is the picture of a pivot on a graph. And what it actually does is a so you no.
So I'm hopeful that Louis will be able to rejoin the broadcast shortly, but maybe while we are waiting for that to happen, those of you who have questions so far can type them into the Slack, and we can pick up some discussion there.
Okay. Am I back from the dead?
Looks like you're back, Louis. Please carry on.
Okay. Thank you. I'm sorry for
You need
this.
to go back a couple of points in your slides.
Okay. Do you know how many points, or maybe I just start this slide again?
That would be perfect. Yeah.
Okay. So, well, do you remember bank boxes? No. Okay. So
Yeah, we remember this.
Okay, so now if you remember bank boxes, I can try this time to talk to you about a simpler version of the HH rule, where not only Q is a Boolean polynomial, but R is also a Boolean polynomial. So not any polynomial. So we're not going to care about faces. So in this diagram, you have H boxes with well, without faces. So this is a normal pivot, we would say, so a pivot on a graph. And what this rule applies actually is a hyperpivot. So you can also bang box the variables. A more detailed version is this. So here you can see that you can find back those variables y0 and y1 corresponding to the 2h from the rule. Y0 is connected to the Q part of the circuit of the diagram, and Y1 is connected to the R part of the diagram. And when they cancel each other, the result here is the product in the phase of Q and R. So any monomial in Q is connected to every monomial in R. So it does this diagram. If you still don't like bang boxes, I have this example where Q is actually so the sum of one variable and the product of two variables, and R is the sum of three variables. And this part of Q is then connected through H boxes to every variable that contain R. But this does not picture completely the HH rule. So to do this, we need the graphical Fourier transform, which is some very useful tool introduced by Stach, John, and Alex a year ago. And this graphical Fourier transform featuring the hyperpivots creates the Fourier hyperpivots. So thanks, Alex, for the picture. And so for some detail in the in the real in the complete HH rule, here S and T are well, are any real polynomial. So you in this polynomial you have any phase in H. So what happens is that those phases kind of develop into the monomials in Q and create this. If you want to understand what it means, I guess you need to read the paper. It is well detailed and explained, but I don't have time to do it here. What is satisfying that you have like 4 overlapped bank boxes, and another satisfying thing is that we were able to prove this equality inside ZH calculus. So it's not only true because it is the translation of the HH law of a Pathom rule, but we were also able to prove it in ZH calculus. In the same idea, the omega rule is some local complementation. This is local complementation, and it is actually hyperlocal complementation. So you have groups of variables which corresponds to the monomials in the polynomial. And the final rule, so as I said, it's really ugly, and it's, well, I don't know. You make your choice about this one. So I find it very beautiful because I've spent quite some time to find it. But it's called the case hyperpivot because it comes from the case rule. And well, here it is. The interesting part of this this equality is that we also were able to prove into ZH calculus, and you can prove it only using Fourier hyperpivots. And actually, those two diagrams that you see are coming from one diagram on which you apply HH rules, and depending on which variables you choose to HH on, you can end up with this diagram or the other, which is what I want to conclude with. Is that if you wanted to find new rules for path sum or for verification of circuits in general, you can come from one expression which can be reduced in different ways, and if one of these terms, so for example B has less variables than C, you can create a new rule from B to C. Another thing that could add new rules for verification is the different equalities that ZH have and that ZH has, and not path sum. So, for example, the author rule, which is present in the basic rule of ZH calculus, can end up with a new rule in the path sum framework. Thank you.
Woo! Thank you, Louis. The most exciting talk of the meeting so far. Very stimulating. Because of the introduction, I think we'll keep the questions down to one question, which Mehdi asked during the this short pause in the middle, which is that is there any link between the hypergraph forms and factor graphs, which are used to decompose probability as products?
Okay, I'm sorry, I don't know anything about these, so.
Okay, in that case, let's see. I think there is no other question which will be short to ask, so I will stop the online discussion there. Oh, Matt Amy says, how difficult is it to rewrite diagrams with bang boxes?
To rewrite. Okay. I don't get the question.
Okay, well, let's perhaps take offline for discussion, because as we've seen from some of the banter, it's one PhD per dot in these kinds of setups. So the answer is probably quite complex, but I expect that Alex and Vladimir and various others have something to say on that. So with that one, I will thank you to Louis again, and let's turn off this video, and we will go in a couple of minutes to the final talk of the session. Thank you.
Thank you.